So next, what I wanted to discuss is I want to bring together the ideas that we've been developing about the particles, about the particle states, and they are we have seen that these operators act on some Hilbert space, and the states in that Hilbert space have the interpretation of being particle states. So this Hilbert space has a special name, and it's called the Fock space. And let me just discuss the properties of Fock space. So Fock space is the Hilbert space of quantum states spanned by the creation operators A dagger and a B dagger if there are complex scalar fields. So Fock space is a Hilbert space, and it consists of A dagger K or B dagger K, acting on the vacuum. We mean multiple A dagger and B dagger, so we put S's there. So that's what the Fock space is. And it has the following properties. Number one is that the states such as say K1, K2, dot 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 Kn. So these are. So this is the here I mean this is Hilbert space, not the Hamiltonian density. So I'm putting a tilde on it. So one of the first property of Fock space is that these states are eigenstates of Hamiltonian and the momentum operator. So the energy momentum operator with eigenvalues say k mu 1 plus k mu 2 dot 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 k mu n. So if it's the energy, then of course we put all the mu equals to 0. If it's momentum, then we put mu equals to I, where I goes from 1, 2, 3. So these are four momentum eigenstates in the momentum space. So if you take the Fourier transform, what would they give rise to in position space? So in position space, these states are represented by a wave function, which we are labeling in terms of the three momentum set. They would be given by, up to some normalization, a plane wave state with energy given by the sum of all the energies plus the momentum part given by the sum of all the momentum dotted with x. So you'll recognize this as the plane wave. So in other words, the particle, although these has particle interpretation because their energies and momentum add up as you add more and more particles by applying the creation operators, in position space they're completely delocalized. So they are completely delocalized. Where in momentum space they're like delta functions. Okay, that's comment number one. Number two is that we assume that the vacuum is a Lorentz invariant quantity and it's normalized. Okay, so we assume the vacuum is normalized. If it's normalized, then what happens to the particle states. So let's take the state with one particle. Its normalization can be calculated. So this is A K1, A dagger of K1 acting on the vacuum and its conjugate. Now if I apply the canonical commutation relationship to this, I'm going to get two terms. One of the term is going to vanish. So the term with A dagger of K1 and A of, okay, let me just take them to be different. Let's just take this to be K2. So this would be K2. So then if I do a commutation relationship, then this would be K2 and this would be K1. And then I'm going to get a term where we're going to get 2 pi cubed of 2 of EK1. It doesn't matter if it's EK1 or EK2 because it's multiplied by a delta function, which is only non-zero when K1 is equal to K2 times the inner product of vacuum. And this is going to be 1. And this guy acting on here is going to give me 0, and this acting on this is also 0. So only the second term will survive. And the second term has the form of 2 pi cubed 2 of EK1 delta cubed K1 minus K2. So, and then what we can do is that we can take our state K1, K1, K2, and we can integrate it over all of momentum space. And it doesn't matter if you're doing it over K1 or K2. Then, as we can see, with this delta function, replacing this thing, this is going to be exactly 1. So if we assume that our vacuum is normalized, the excited states are also normalized when you integrate it over all of the momentum space. And this is essentially the orthonormality condition. So this is the orthonormality condition of the particle states. The other thing you can easily verify that states with different number of particles are orthonormal. So if you have a state with 2 particles, say K1 and K2 momentum, 3 momentum, and then you take the inner product with a state which has only 1 particle, because of the number of creation and annihilation operators being different, you can easily show that this is 0. So the Fock space, by which, let me just denote it by this, it's a direct sum of the vacuum, which is, I write it as H0, the Hilbert space, and then the Hilbert space of 1 particle plus the Hilbert space of 2 particles, so on and so forth, and it goes on. So this is the Fock space. So the Fock space is an infinite dimensional Hilbert space where each component of the Hilbert space, apart from this guy, each component of the Hilbert space themselves are infinite dimensional because the momentum has infinite range. But this is the mathematical structure of the Fock space. Now, for scalar fields, we saw that if I take a 2-particle state, say with K1 and K2 momentum, then if I exchange the 2 particles, they are symmetric. So this is a consequence of the commutation relationship that the commutator of A dagger K1 and A dagger K2 is 0. So this gives rise to Bose statistics. So these are bosons. We're dealing with bosons. And finally, we saw that the transformation of the fields, so the transformation of the quantum fields are opposite to those of the classical fields.